So when you do the scaled object train with psi plus 10 classes DC and subset. Okay. What's the definition of scaled objective sphere? In section 4.2. Yeah. So that's the scaled objective sphere. Okay. So you can, once you define your objective sphere, you have to define what to threshold, right? So you can threshold the softmax output, which is supposed to be low for these classes and very high in the correct class for these examples. But then they say that it's more reasonable and justifiable to threshold that instead of the softmax. Of course, you can't use this in the other algorithms, but I mean they do have a let's say honesty point, because they did compare with just thresholding that. So that's good honesty points for them. And then they showed that, well, if you threshold that, it becomes even better.
But one question, maybe like more for the application of this type of approaches, because I was, how I say, like as if, because your unknowns can be infinite, right?
Yeah.
But basically, this type of approach would help you maybe understanding that some of your unknowns are actually targets. If they are, for example, for the data set of the street view numbers, because some houses have numbers, but maybe some other ones have letters. So letters are not numbers. So maybe that belongs to the unknowns.
Yeah.
So maybe this method, I don't know, in my head would be like hyper useful if all of the sudden it helps you bringing elements of A into C.
Yeah, so one of the things...
And does it do it, or... And besides, because also how do you define it? Because at the end of the day, everything you put is finite, right?
Yeah.
So A will be also finite, because they are elements of your...
A is, by definition, it's infinite, because it's everything out there. So it's any classification target.
Okay.
So it is infinite, but yeah, that's a good point in that. So all of the papers that we did in the series, they do not address the problem of what to do with the unknowns. Like that is left to the reader, to the application, to whatever you're doing. What they provide is a way to identify the unknowns, and that is the contribution of the papers. What to do with the unknowns, I guess it's going to depend on your particular application. Like if you want to assess if they should go into the training set, or if you should just ignore them, or if you should not give a prediction for them, or give a fixed prediction on them, or base your prediction on something else. That's an open-ended question, I think. Yeah.
What was the problem with the loss function? What was your remark with the loss function? You said somebody didn't like it, or the loss function?
No, the loss function is fine. It's just they call it objective sphere. It's a regularizer.
Do you think is there any way to do something similar with the regression, or to generalize that?
Not like this.
Yeah, it's
not like this specifically, because it's designed for, like, in regression there are no classes.
Yeah.
Right? It's just trying to predict a function. So for regression, it's better the methods like the MC dropout or more Bayesian approaches that actually give you an estimate of uncertainty, like a real estimate of uncertainty. This one, it's also curious. It's not giving an estimate of uncertainty. There's no number to it. It's just saying this is an unknown class. MC dropout did give a good estimate of actual uncertainty. Same open max. It gives a measurement of uncertainty, so you can decide how to interpret it. Right?
How do you relate it, or do you relate it to meta learning approaches? Where you learn on classes that you see, and then you expose to new classes that you don't know. If the case is that the unknowns are just the two classes, there might be a kind of relationship. What do you think about that?
Well, I think it's related to what you said before. I think you can use these approaches to identify the unknown classes, but then you need an extra algorithm to sort those classes out. So I think it can be helpful if you're actually trying to do meta learning. You're trying to learn new classes on the go. This can at least tell you with a good degree of certainty that this is nothing like what you trained on.
Spot them if,
Yeah. This is more a spotting mechanism rather than trying to learn new things. Yeah.
One thing about the entropy of the loss in the objective sphere, like given that they add our regularization to the objective sphere, do you even need to start with entropy open set loss? Because like the entropy open set loss has something on the as a loss in the background class tries to make the softmax flat, but then with the regularization you will still get to the f becomes 0, and 0 gives you already a flat softmax.
Yeah. So what they argue here is that this is needed to make this loss have a unique minimum. So what they don't guarantee, which is so it's at the end of their proof before. So the theorem does not show that f equals 0 is the only minimum because it is possible that there exists a subspace and so on. So it may, but it doesn't have to result in a small magnitude of unknown inputs.
Yeah, just like since the regularization makes x 0, then you automatically get
it's reciprocal.
basically the regularization makes x 0, and actually you get 0 makes all the softmax input 1 over 2. So you wouldn't need to add the extra term you get.
You say that this regularization makes
X 0 for background objects.
Yes.
And so if f is 0, then the softmax becomes 1 over c for all classes, and so you don't need to modify the original cost function again.
But you know, my guess, even if the absolute norm of DS is very, very small, because the softmax, we always derive a
Yeah, the softmax normalizes, right?
The absolute code is not exactly 0. So it's very, very small, but you have like 1,000 here, and then you will still have a deviation, so it's not the same thing exactly.
And then the softmax normalizes, right? So it's always going to be.
To provide the standard.
So you have to guarantee that they will be flat and then that they will be small. That the feature activation is going to be small. Yeah. Okay. Cool.